In this dry friction problem, we're asked to determine the maximum force P that can be applied without causing movement of the 250-pound crate shown that has a center of gravity at point G. And they tell us that the coefficient of static friction at the floor, and that's between the bottom of the crate and the floor, is 0.4. So this problem falls into the group of problems known as impending motion at some points of contact, like we discussed in the lecture. And the reason for that is that there are two cases for movement or motion here. Case one is where the crate slips, or we'll say slipping occurs. Case two is where the crate tips over, or tipping occurs. So our approach to the problem then is to solve for the maximum force P for each individual case, and then compare the values of P obtained, and the case with the smaller value of P is the case that will actually occur. So let's look at slipping first, and we'll draw a free body diagram for that. And I'm going to show 250 pounds downward from G. I'm going to show the force P. I'm going to show the normal force N. And then when slipping is just about to occur, then we're in the state of impending motion. And as we discussed in the lecture, when we're at that point of impending motion, the frictional force is going to be at its maximum, and it's going to equal it's going to be the limiting static frictional force, F sub S. And we know that we can express that as mu sub S times N. And they gave us mu sub S, so F sub S is equal to 0.4 N. So the frictional force is a function of the normal force, so we don't have that extra unknown. Now I didn't put any dimensions on here because we won't need to write a moment equation to solve for P here. We can sum forces in the y direction. And assuming that upward is positive, we'll have the weight acting downward plus N. So pretty simply, N equals 250 pounds. And then summing forces in the x direction, we have P minus F sub s, which is 0.4 n, and we know n is 250 pounds. So we solve for P and find that P is equal to 100 pounds, meaning that when P is equal to 100 pounds, we have impending motion. So if P gets just a little bit larger, then the crate will start to slide. Okay, so we want to remember that number. P for slipping is 100 pounds. Now let's do the tipping case. Draw another free body diagram for tipping. I'm going to need some dimensions on this one. I'll show the weight at G and the distance from G to the front of the crate, or the right side of the crate, right edge of the crate, is 1.5 feet. I'll show P. P is 4.5 feet away from the ground. Now, the key to these tipping type problems, or the tipping case, is to realize that when you have tipping impending motion, that the normal force is going to be concentrated on the, in this case, the right edge of the crate. In other words, for impending motion, for tipping, when you're applying a force P to the left side of the crate, when it just starts to tip, it's going to tip over or about this edge here. So all of as it starts to tip and the back lifts off, the back of the crate lifts off the ground, you know, there's no contact with the ground. The crate does not contact the ground except along the front edge. I showed. So the normal force is going to be concentrated there. And the frictional force is also going to be concentrated there. And that frictional force is the same as it was in the slipping case. It's going to be F sub s equals 0.4 times the normal force. And we'll see that the normal force, the magnitude of the normal force, isn't going to change. It's still going to be the weight, but we will go through that again and show that. So let's sum forces in the y direction. We have 250 downwards plus N. So the normal force, just like in the slipping case, is 250 pounds. Now let's sum forces in the, well, we're not going to sum forces in the x direction. Now we're going to sum moments about the tipping point. So let's sum moments, and that point was, that was point A. I'll put that on here. Sum moments about A. It's impending motion, so it hasn't tipped yet, but it's just on the verge. So the crate is still in equilibrium, but it's getting ready to leave equilibrium. So the sum of the moments about A, assuming counterclockwise positive, is going to be the 250-pound weight force times the perpendicular distance from A. So it's going to be 250 times 1.5, and that's a positive moment about A, minus P times its perpendicular distance from A, 4.5, and that's a negative moment because it acts clockwise about A. And we solve for P, and we get 83.3 pounds. We compare those two values of P. It will take 100 pounds to get the crate to slip, to get the crate to slip, to start sliding, but only 83.3 pounds to get it to tip. So it will tip before it slips, and therefore the maximum force that can be applied to the crate without causing movement is the 83.3 pounds.